Tonight, we're going to talk about a possibility that physics, actual physics, not science fiction, not philosophy on its own, suggests might be true. The idea that there is another version of you out there, not a vague spiritual twin, not a metaphor, a real, physical person built from the same atoms, living inside the same universe we all share, who either is you in every single way, or differs from you in exactly one small choice they made this morning, or is you but with a completely different life, depending on which layer of this we're talking about. And there are multiple layers. Before we get into this, if you've ever sat with a question that made the room feel slightly different afterward, the kind of question you carry around for days, take a second to like the video or subscribe. It's a simple thing, and it helps this channel reach more people who think about exactly these kinds of ideas. Now, let's go. Here's what most people assume. They assume the universe is large, but finite. They assume there's one of everything, one Earth, one sun, one history, one version of you. They assume that even if the universe is too big to ever fully explore, there is still in some sense a single copy of reality, one set of facts, one truth about what exists. And that assumption feels reasonable. It matches everything we experience. You've never met another version of yourself. You've never encountered an alternate Earth, so the natural conclusion is that there isn't one. But here is where it gets interesting. The assumption that there's one of everything is not based on evidence, it's based on the absence of evidence, and those are very different things. We have never detected a duplicate Earth, but we've also never been able to look at anything more than a tiny sliver of what might actually exist. The universe could be unimaginably larger than what we can see, and if it is, then the rules of mathematics and probability start doing something that makes most people genuinely uncomfortable when they sit with it long enough. By the end of tonight, you're going to see your own existence very differently, not in an unsettling way, more in the way that you see a familiar room differently after someone tells you something true about its history that you didn't know before. The room is the same, but it isn't anymore. Let's start at the beginning. When most people think about the universe, they picture something large, and it is large. The observable universe, meaning the part of the universe whose light has had time to reach us since the Big Bang, is about 93 billion light-years across. That number, 93 billion light-years, needs to land properly before we move on. 1 light-year is about 5.9 trillion miles, so 93 billion light-years is roughly 550 sextillion miles. That's a 5, followed by 23 zeros, written in miles. If you drove a car at highway speed for every second since the universe began, you would have covered about 1 trillion miles. You would need to do that drive roughly 550 billion trillion times to cross the observable universe. It's a number so large it stops feeling like a number. And that's just the observable part. The observable universe is defined by a limit. It's the bubble of space from which light has had time to reach us. The universe is roughly 13.8 billion years old. Light travels at about 186,000 miles per second, fast enough to circle the Earth about 7.5 times in a single second. But because the universe has been expanding this entire time, the light from the most distant objects we can see has been traveling toward us for nearly 13.8 billion years, and yet those objects are now about 46 billion light years away. That's not a contradiction, it's just what expansion does. The space between here and there has been stretching while the light was in transit, like a message written on a rubber band that someone's been pulling apart the entire time it was being delivered. So 46 billion light years is the radius of our observable universe. The full diameter is about 93 billion light years. But here is the thing most people don't fully sit with. That boundary, the edge of what we can observe, is not the edge of what exists. It's the edge of what we can see from here, right now, given how long the universe has been around and how fast light travels. Beyond that boundary, space almost certainly continues. The question is how far. And depending on how you answer that question, everything else about this conversation changes. There are two possibilities. Either the universe is finite, meaning it has some total size and eventually ends, or it is infinite, meaning it genuinely goes on forever in all directions. If it's finite, we need to understand what that even means and what happens at the edge. If it's infinite, then mathematics has some genuinely unsettling things to say about what must exist out there. We'll come back to infinity. First, let's talk about what we actually know. We know the universe is at least as large as what we can observe. That's a tautology, but we have some clues that suggest it's vastly larger. One of the best clues comes from something called the curvature of space. Space can be curved. This isn't a metaphor. Physical space, the fabric of reality itself, can have a geometry. Think about the surface of the Earth. If you draw a triangle on a flat piece of paper, the angles add up to exactly 180 degrees. But if you draw a triangle on the surface of the Earth, using great circle arcs as your sides, the angles add up to more than 180 degrees. That's because the surface of the Earth is positively curved. It bends back on itself. A negatively curved space, shaped like a saddle, would give you triangles whose angles add up to less than 180 degrees. Now here's the thing, we can measure the curvature of our universe. We do this by looking at the cosmic microwave background, which is the faint glow of radiation left over from the early universe when it was about 380,000 years old. That radiation contains subtle patterns, like fingerprints in the earliest structure of space, and the size and shape of those patterns tells us about the geometry of space itself. When we measure it, what do we find? Flat. The universe, as best we can tell, has almost no curvature. The angles in cosmic triangles add up to 180 degrees. We can measure this to within about 0.4% certainty. The universe is, to the precision of our instruments, geometrically flat. Now here's why that matters. If the universe is perfectly flat, and if it's also simply connected, meaning it doesn't fold back on itself like a torus or a more exotic shape, then it is almost certainly infinite. A flat, simply connected space goes on forever in every direction, and we have no evidence that the universe folds back on itself. Some cosmologists have suggested it might, and some observations could hint at that, but the current consensus leans toward an open, flat universe that just keeps going. We don't know this with certainty, but the best current understanding of cosmology suggests the universe is either infinite or so large that the difference between infinite and just really, really big doesn't matter for any practical calculation. Some estimates, based on the observed flatness combined with our best models of inflation, suggest the entire universe could be at least 10 to the power of 10,000 times larger than what we can observe. That number, 10 to the power of 10 quintillion, is not something the human brain was built to process. Let me try to give you some sense of it anyway. The observable universe contains roughly 2 trillion galaxies. Each galaxy contains on average about 100 billion stars. That's 2 trillion times 100 billion stars in the observable universe alone. If the full universe is 10 to the power of 10 quintillion times larger, then the number of stars in the full universe compared to the number of atoms in the observable universe is like comparing the entire ocean to a single molecule of water. The observable universe would be less than a single atom against the backdrop of what might actually be out there. That's assuming the universe is flat and simply connected and infinite. We don't know for sure, but if it is, here is where mathematics starts saying something that most people aren't ready for. Infinity is not just a big number, it's a fundamentally different thing. Most people treat infinity as if it's just a really large quantity, something you can imagine by scaling up. But infinity is not like that. Infinity has rules that normal numbers don't have, and those rules lead to conclusions that feel impossible but are mathematically sound. Here is one of those rules. If something has a non-zero probability of happening, and if you repeat the situation an infinite number of times, then that thing will happen. Not probably, not eventually in some vague sense. It will happen, an infinite number of times. Let's make that concrete. Imagine you have a fair coin and you flip it. The probability of getting heads is 50%. If you flip the coin 10 times, you might not get heads at all, or you might get it all 10 times. If you flip it 1,000,000 times, you'll get very close to 500,000 heads. If you flip it an infinite number of times, you will get heads an infinite number of times, not approximately infinite, exactly infinite, and you will also get tails an infinite number of times. Both of those infinite things happen simultaneously, with certainty. Now replace coin flip with region of space identical to our observable universe. Here's how that works. Our observable universe, the 93 billion light-year bubble we live in, is a specific arrangement of matter and energy. Atoms arranged in specific patterns, stars in specific locations, planets orbiting in specific ways. Us here having this conversation, in this particular configuration of space and time. This configuration, as complex and specific as it is not infinitely complex. It is made of a finite number of particles. There are roughly 10 to the power of 80 atoms in the observable universe. 10 to the 80th power is a lot. Written out, it's a 1 followed by 80 zeros, which is a number so large that if every atom in the universe were a digit, you couldn't write it. But it is finite. A finite number of particles can only arrange themselves in a finite number of ways. The number of possible arrangements is enormous, but it is bounded. Physicists sometimes describe this in terms of quantum states. The observable universe exists in some specific quantum state. The total number of possible quantum states for a region of space this size has been estimated at 10 to the power of 10 to the power of 118. That's 10 raised to the power of a number that already has 118 digits. It is by any standard of human comprehension a number beyond numbers. And yet it is finite. If space is infinite, and if matter and energy are distributed throughout that infinite space at roughly the same average density we observe in our own region, which is our best current assumption, then every possible quantum state for a region this size must be realized somewhere out there. Not probably, necessarily, because you have infinitely many chances to hit each finite configuration, and any finite target hit by infinitely many chances is a certainty. This is not a metaphor, this is arithmetic. And one of those finite configurations is identical to ours. In fact, if space is truly infinite, there are infinitely many regions of space that are in exactly the same quantum state as our observable universe, meaning the same particles, the same stars, the same Earth, the same you, not similar, identical, down to the position of every atom in your brain as you're reading or listening to this right now. The physicist Max Tegmark, who has thought about this more carefully than almost anyone, estimates that the nearest identical copy of our observable universe is about 10 to the power of 10 to the power of 118 meters away. That's not a distance with a convenient comparison, because no comparison exists for it in ordinary human life. The entire observable universe is about 8.8 times 10 to the power of 26 meters across. So the distance to your nearest cosmic twin is so much larger than the observable universe that it would take more zeros to write the difference than there are atoms in everything we can see. But if space is infinite, that distance is irrelevant. Distance in an infinite space is not a barrier to existence. Your twin is there. There is another you right now who has read this exact sentence and is having the same thought you are having about reading this sentence. That's the level 1 multiverse, and it's the most conservative version of this idea. It doesn't require any exotic new physics. It doesn't require parallel dimensions or quantum branching or anything strange. It just requires that the universe is large enough, and our best current physics suggests that it probably is. At this point, most people have an objection. It goes something like this. Okay, even if space is infinite, How do we know matter keeps going past what we can observe? Maybe our observable universe is a rare island in an otherwise empty void. Maybe beyond the cosmic horizon there's just nothing, or empty space, or some completely different kind of structure we can't predict. This is a fair question. We genuinely can't observe what's beyond our horizon. That's what the horizon means. So we're making an assumption when we extend our local physics outward. But here's why that assumption isn't arbitrary. The universe we observe looks remarkably uniform on large scales. When you zoom out far enough, averaging over distances of about 300 million light years or more, the universe looks pretty much the same in every direction and at every point we can sample. The density of matter, the distribution of galaxies, the large-scale structure of cosmic web filaments and voids, it's all consistent with a universe that is roughly homogeneous and isotropic. Homogeneous means the same everywhere. Isotropic means the same in every direction. These two properties together are called the cosmological principle, and it's the bedrock assumption of modern cosmology. If the cosmological principle holds, then the universe beyond our horizon should look broadly similar to the universe inside it. Matter should continue to exist, galaxies should continue to form, stars and planets should continue to arise, and the same physical laws should govern all of it, because those laws appear to be universal within everything we can observe. Is this guaranteed? No. We can't prove the cosmological principle beyond our horizon. It's an extrapolation, but it's a well-motivated one, supported by everything we know about physics and by the way the universe looks in every direction we can point a telescope. So the most reasonable current picture is that beyond our observable bubble, space continues, matter continues, galaxies continue, and the physics continues to be the same, which means the conditions for life, for planets, for stars, for whatever arrangements of matter are needed to produce something like a human mind, those conditions should persist out there. And if they do, in an infinite space, every arrangement of matter that can occur will occur, including this one. There's another version of the objection, and it's more subtle. It goes, even if there are other regions of space with the same arrangement of matter, quantum mechanics means that there's always some fundamental randomness that prevents true perfect copies. Every quantum system has inherent uncertainty. So how can two regions be truly identical, down to the quantum state? This is a real complication. Quantum mechanics does introduce genuine randomness. But here's the thing. The argument about infinite copies isn't based on identical quantum states in a hidden variable sense. It's based on quantum states in the many worlds or wave function sense. And when you account for that properly, the conclusion actually gets stronger, not weaker. We'll come to that in a while. But the short answer is that quantum mechanics doesn't rescue us from cosmic twins. If anything, it multiplies them. Let's keep building. We need to talk about inflation. Not the economic kind, the cosmological kind. Because inflation is the reason the universe might be so unimaginably large. And once you understand inflation, the possibility of infinite copies stops being an exotic hypothesis and starts being a fairly natural consequence of the physics we think we understand. The very early universe, in the first tiny fraction of a second after the Big Bang, was in an extremely hot, dense state. We understand this phase reasonably well through the standard model of particle physics and general relativity, but there's a period even earlier than that, before the universe was about 10 to the negative 32 seconds old, which is 100 trillion times shorter than the blink of an eye, during which cosmologists believe something dramatic happened. During this period, the universe underwent a phase of exponential expansion. Not fast expansion, exponential expansion. There's a difference. Fast expansion is when things get bigger quickly. Exponential expansion is when things get bigger by a constant factor in every equal unit of time, like compound interest but for the entire universe. In practice, this means the universe doubled in size repeatedly in rapid succession, expanding by a factor of at least 10 to the power of 26 in a time period of roughly 10 to the negative 32 seconds. That expansion factor, 10 to the 26th, means the universe grew from something smaller than a proton to something roughly the size of a grapefruit in a moment shorter than any clock has ever measured. Why does this matter? Because inflation solves several major puzzles about our universe. It explains why the universe is so flat. It explains why the cosmic microwave background looks so uniform. It explains the absence of certain exotic relics that should have been produced in huge quantities in the very early universe, but which we never observe. All of these puzzles have natural solutions if the universe went through a period of exponential expansion. But inflation also has a consequence that most people don't think about. Once it starts, inflation is very hard to stop. Here's the idea. The exponential expansion during inflation was driven by some field or form of energy, often called the inflaton field, that had a very high energy density and caused space to expand rapidly. As inflation proceeds, this field slowly rolls toward a lower energy state, and when it reaches the bottom of that energy landscape, inflation stops in that region, and ordinary Big Bang physics takes over. But here's where it gets interesting. Quantum mechanics introduces fluctuations in the inflaton field. In some regions, quantum fluctuations push the field to higher values rather than lower ones, causing inflation to continue, even accelerate, in those regions. In other regions, the field rolls downward and inflation ends. The net result is that inflation, once started, never really stops everywhere. It ends locally, in patches, producing separate regions of completed inflation that each become something like a Big Bang, a separate expanding universe. But in the space between those regions and beyond them, inflation keeps going, constantly generating new regions where it ends, and new Big Bangs ignite. This is called eternal inflation, and it's the standard prediction of almost every inflationary model cosmologists have worked with. The universe in this picture is not a single bubble that expanded and cooled. It's an endlessly frothing sea of inflationary expansion, from which isolated bubbles of completed inflation detach and become separate universes, each with their own Big Bang, their own initial conditions, their own subsequent history. We live inside one of those bubbles, what we call the universe, the entire 93 billion light-year observable sphere, plus everything beyond our horizon, is one pocket of completed inflation in a much vaster structure of ongoing inflation. And that structure produces new pockets, new universes, constantly and without end. Some of these other pockets might have identical physics to ours. Some might have different physics, different values for the fundamental constants of nature, different numbers of spatial dimensions, different laws. This is the level 2 multiverse, and it's a step beyond the simple infinite space argument. We'll come back to it. But first, let's understand what inflation does to our own universe. Even within our own bubble, if inflation produced the right conditions, the total extent of space in our pocket universe alone could be almost incomprehensibly large. The exact number depends on how long inflation lasted and the details of the inflaton field, but in many models, our own pocket universe is vastly larger than the 93 billion light-year observable sphere. Some estimates put it at 10 to the power of 10 to the power of 118 meters across, the same number Tegmark quotes for the distance to our nearest cosmic twin. That's not a coincidence. It's the reason that twin could exist within our own universe without needing any exotic physics at all. The universe we live in, according to this picture, is almost certainly infinite. And in an infinite universe, we are not alone in any sense of the word. Let's slow down here, because this is where the abstract becomes genuinely personal. We've established that in an infinite or near infinite universe with uniform physics, identical copies of our observable universe almost certainly exist. That means identical copies of everything in it, including you. But what does that mean? What does it mean for there to be another person who is, in every physical sense, you? The first thing to be clear about is what identical means in this context. We're not talking about a person who looks like you. We're not talking about a person who shares your personality traits or your memories in some vague sense. We're talking about a person whose brain contains the exact same arrangement of neurons, synapses, and electrochemical states as yours. A person who has lived the exact same life you've lived, made the exact same choices, had the exact same experiences, formed the exact same memories. A person who, if you could somehow be placed side by side, would be indistinguishable from you in every physical measurement. That person at this moment is reading or listening to this exact passage. They're having the same thought you're having right now. They're skeptical of the same parts you're skeptical of. They're interested in the same parts you're interested in. They are, by every physical criterion we know of, you. Now here's the question that follows naturally. Are they you, or are they just someone identical to you? This is not a trivial question. It touches something deep about what identity even means. Most of us think of ourselves as continuous entities with unique histories. There is one version of you, the one that started in a specific body on a specific day, and that version has persisted through time, through all the experiences and changes, maintaining some core thread of continuity. That continuity is what we mean by personal identity. But if there's another physical being with the same history, the same memories, the same neural configuration, what does that continuity even mean? Are you both the same person? Are you two different people who happen to be physically identical? Is personal identity something that physics can even describe? Or is it something that lives in the gap between the physical facts and our experience of them? Philosophers have thought about this for a long time. Derek Parfit, one of the most important philosophers of the 20th century, spent decades examining exactly this kind of question. And his conclusion was quietly devastating. Personal identity, he argued, is not what we think it is. When we say, "I am the same person I was 10 years ago," we're making a claim that seems obvious, but actually rests on very thin foundations. Our bodies have changed. Many of our beliefs have changed. Our memories are unreliable reconstructions. The only thing that gives us a sense of continuous identity is the narrative we construct about ourselves. And narratives are not the same as metaphysical facts. If Parfit is right, then the question, "Is my cosmic twin me?" might not have a clean answer. Because the question, "Am I me?" might not have a clean answer either. Identity might be more like a useful fiction, a story we tell to organize our experience, rather than a deep fact about the universe. That's uncomfortable. Most of us feel very strongly that we exist as a continuous, unique individual. That feeling is real, but feelings are not always reliable guides to metaphysical truth. The fact that you feel continuous doesn't prove that continuity is a deep feature of reality. It might just prove that your brain is very good at constructing the experience of continuity. We'll return to this, but first, let's add another layer. Here's something the pure infinity argument implies that most people don't think through fully. It's not just that there are identical copies of you in an infinite universe. There are also near copies, every possible variation of you. In an infinite space with all possible arrangements of matter realized, there is a version of you who made every choice you've ever made, but also a version of you who made a different choice at every branch point. There's a version of you who took a different job, a version who said something different in a conversation that changed everything, a version who woke up 5 minutes later this morning, a version who is reading this same material but has slightly different ideas about it because their brain developed slightly differently. And not just one of each, an infinite number of each. That version of you who took a different path exists an infinite number of times in infinitely many distant regions of the universe, just as you exist an infinite number of times. And each of those versions also has infinite copies, and each of those copies is having their own experience of being the one and only version of themselves. This is not science fiction. This is what infinite space plus uniform physics implies. The math is high school level probability applied to cosmological scales. Now you might be wondering, does this mean everything that could have happened to me did happen to some version of me? Yes, if the possibilities are all physically realizable, if they don't violate the laws of physics, then in an infinite universe, every possible life history that is physically possible is being lived by some version of you an infinite number of times. There is a version of you who became a painter instead of whatever you are now. There is a version of you who never found the thing that matters most to you. There is a version of you for whom everything worked out in every way simultaneously, and a version for whom nothing did. There is a version of you listening to this right now who has never heard of the concept of a multiverse, and it's striking them like something new and unsettling. And a version for whom this is old news, and they're listening anyway because they like the voice. All of this, in an infinite universe, is real. Not metaphorically real, physically real. Arranged out of atoms and energy, governed by the same laws that govern you, separated from you only by distance. Distance that will never be crossed and cannot be observed, and will never allow any communication or awareness between you and them. They are real and they are unreachable. That's perhaps the strangest part of this. Your cosmic twins are not in some distant dimension. They're in our universe, made of the same stuff, separated from you by nothing more than space. But that space is so vast that you might as well be in different universes. Light from their location will never reach you in your lifetime, or in the lifetime of the universe. You will never know each other, even though you are the same. We need to pause for a moment and be honest about a real conceptual problem. Infinity is extremely useful in mathematics, but it may not actually describe anything physical, and if the universe is not truly infinite, just very large, then the argument for cosmic twins weakens significantly. Some physicists are uncomfortable with actual infinity in physical theories. They argue that in the real world, things are quantized. Space might not be continuous, it might be made of discrete units at the Planck scale, which is about 10 to the negative 35 meters. If that's the smallest meaningful unit of space, a very, very small number, then any finite volume of space contains a finite number of distinct locations. And a finite volume can only hold finitely many configurations of matter. This doesn't rule out cosmic twins, but it does change the calculation. More importantly, even if space is geometrically infinite in principle, we don't know that matter and energy extend infinitely. The cosmological principle is an assumption. It's a well-motivated assumption based on what we observe, but it's an extrapolation beyond what we can verify. It's possible, though many cosmologists consider it unlikely, that our observable universe is in some sense special, a rare island of complex structure in a vast emptiness. There's also a more subtle problem with how we reason about infinity. When we say in an infinite universe every possible configuration must occur, we're using a form of reasoning that works cleanly for simple probability over discrete outcomes. But physical configurations of the universe are not like coin flips. They're distributed across space in ways that depend on the physics, the boundary conditions, and the specific geometry. Whether an infinite space with uniform average density guarantees every possible local configuration is a more technical question than it first appears. This is not a fatal objection, but it's a real one. The argument for cosmic twins is best understood not as a proof, but as a prediction of certain cosmological models. Specifically, it's a prediction of models that include infinite flat space, with the cosmological principle holding everywhere. If those models are right, cosmic twins are real. If those models need to be modified, the prediction might change. What we can say with confidence is this: either the universe is infinite and the argument holds, or it's finite and we need to understand what that means for cosmology. Either way, we're dealing with questions of a scope that human beings have barely begun to understand, and either way, the universe is almost certainly not what most people think it is. Let's keep going, because the infinite space argument is actually the most conservative and least exotic version of the possibility of multiple U's. The next version is stranger. We talked earlier about eternal inflation, the idea that the inflaton field drives ongoing exponential expansion in most of the universe, while inflation ends locally in pockets that become separate Big Bangs. Let's think more carefully about what those separate pockets might be like. In the inflationary picture, when inflation ends in a region and ordinary Big Bang physics takes over, what happens depends on the details of the inflaton field at that moment. And here's the thing, the inflaton field, when it's at different points in its energy landscape, might fall into different valleys, different minima, different stable configurations. Each of those configurations corresponds to different values for what we call the fundamental constants of nature. The fundamental constants are things like the strength of gravity, the mass of an electron, the speed of light, the fine structure constant that governs how strongly charged particles interact, the cosmological constant that describes the energy density of empty space. These are numbers that we measure but don't currently understand from first principles. We don't know why gravity is as strong as it is. We don't know why the electron has the mass it has. We just measure these things and use them. In string theory, which is currently the leading candidate for a fundamental theory of everything, there might be something like 10 to the power of 500 different ways the extra dimensions of space can be compactified. Each compactification corresponds to a different set of effective laws of physics, different values for the fundamental constants, different particle content, different forces. This enormous collection of possible universes is called the string landscape. If eternal inflation is real, and if the string landscape is real, then different pockets of inflation might end up in different parts of the landscape. Different pocket universes would have different fundamental physics, different masses, different forces, different constants. Some would have no chemistry because the forces don't work out to allow stable atoms. Some would have no stars because gravity is too strong or too weak. Some would collapse back on themselves too quickly for anything to form. Some would expand too fast for matter to clump into structure. Only a small subset of the possible configurations would allow for galaxies, stars, planets, and the kind of chemistry that produces complex organized systems like living things. This is the Level 2 multiverse, a collection of pocket universes, each with their own Big Bang, each with their own physics, separated from each other not just by distance but by fundamentally different laws of nature. We can't travel between them, can't communicate with them, can't observe them even in principle, not because they're too far away in our kind of space, but because they're separated by the ongoing inflationary expansion that lies between them. Light from those regions will never reach us. This version of the multiverse is much more alien than the Level 1 version. In the Level 1 multiverse, your cosmic twin lives in a universe with exactly the same physics as yours, the same constants, the same laws. They're just far away. In the Level 2 multiverse, most other pocket universes have completely different physics. The electron might not exist in the same form. Hydrogen might not form. The complexity required for anything like you to exist might not be possible. But here's where something called the anthropic principle comes in. The anthropic principle, in its most basic form, just says that we observe the universe to have the properties necessary for us to exist. This sounds trivial, but it isn't. If there are many universes with different physical constants, we can only exist in one of the small subset that has the right constants for our kind of complexity. So of course we find ourselves in such a universe, not because those constants were designed or chosen for us, but because we couldn't be here to observe any other kind. This is actually a powerful idea. There are some features of our universe that seem finely tuned in ways that are hard to understand from first principles. The cosmological constant, the energy density of empty space, is orders of magnitude smaller than particle physics naively predicts it should be. If it were just a little larger, galaxies would never form. If it were a little smaller and negative, the universe would have recollapsed long ago. The observed value seems, from a naive physics perspective, absurdly unlikely. but in a landscape of many universes with different values, it's not surprising that we find ourselves in one with a value compatible with our existence. We're here, so the value must be compatible with our existence. We're just applying the anthropic filter. This doesn't tell us that every other universe is somehow wrong or inferior. It just explains why we observe what we observe, given that we exist. The level 2 multiverse is less directly relevant to the idea of copies of you, because most level 2 universes have such different physics that nothing like you could exist in them. But in those pockets of the level 2 landscape that do have compatible physics, and if there are infinitely many such pockets as eternal inflation predicts, then those universes would themselves be infinite, and they would contain their own level 1 versions of you. So the level 2 multiverse doesn't remove the problem of cosmic twins, it adds layers to it. Now we get to the version of the multiverse that might be the most immediately consequential, because it operates not at cosmological distances, but right here, at every point in space, at every moment in time. This is the many worlds interpretation of quantum mechanics, and it's where the idea of infinite versions of you becomes not just possible, but in this framework, almost unavoidable. Quantum mechanics is our best theory of how reality works at the smallest scales. It describes how particles behave, how atoms form, how light interacts with matter, how the fundamental forces operate. It's been tested more precisely than any other theory in the history of science. Some of its predictions have been verified to an accuracy of about 1 part in a trillion, which is like measuring the distance from New York to Los Angeles to within the width of a human hair. But quantum mechanics has always had an interpretation problem. The mathematics of quantum mechanics describes reality not as a definite state, but as a superposition of many possible states, a wave function that assigns probabilities to all the possible outcomes of any measurement. When you measure a quantum system, the wave function appears to collapse to a single definite outcome. The electron is here, not there. The photon is horizontal, not vertical. Schrödinger's cat is alive, not dead. But the theory itself doesn't describe this collapse. The equations of quantum mechanics describe the wave function evolving smoothly and deterministically. They don't have a collapse mechanism. Physicists in the early days of the theory dealt with this by essentially saying, don't worry about the interpretation, just use the equations to make predictions, and the predictions match experiments. This pragmatic approach is sometimes called shut up and calculate. But the interpretation problem never went away, and in 1957, a graduate student named Hugh Everett proposed a solution that was initially ignored and is now considered by many physicists to be the most natural reading of the quantum formalism. His idea, the collapse never happens. The wave function always evolves according to the equations. There is no special moment when quantum possibilities resolve into classical reality. Instead, every time a quantum system interacts with a measuring device, which is to say every time any physical system interacts with any other physical system in a way that could distinguish between quantum states, the wave function of the combined system branches. All the outcomes happen, but they happen in branches of the wave function that no longer interact with each other. From the perspective of an observer in one branch, the other branches are inaccessible, effectively unreal. But in the global wave function, they're all real. This is the many worlds interpretation, or the Everett interpretation, or the many worlds hypothesis. And here's what it implies for you. Every quantum event that could have gone differently, did go differently, in a branch of the wave function. Every single one. Every time a photon could have reflected or been absorbed. Every time an electron could have jumped to a higher energy level or stayed. Every time a radioactive atom could have decayed or not decayed. At every one of these junctures, which is happening constantly in every cubic centimeter of space, the wave function branches and both outcomes occur. Your brain is a quantum system. The chemical and electrical processes in your neurons involve quantum events. When you make a decision, the physical process underlying that decision involves quantum events. Every quantum branch point in the history of your brain is a moment where a version of you went one way and a version of you went another way. In the many worlds picture, the universe is constantly multiplying. Every moment contains an enormous, possibly infinite, branching of reality into parallel branches that share a common history up to that point but diverge afterward. And every branch contains a complete, fully real version of the people in it, experiencing their branch as the entirety of reality. Right now, in the many worlds picture, there are versions of you who made a different choice at every choice point in your life. Not just the big choices like where to go to school or who to marry. Every choice, every thought that hovered between two possibilities, every moment of hesitation, every reflex that could have gone slightly differently. All of those possibilities are realized in branches of the wave function that are just as real as the one you're experiencing right now. The version of you in another branch who made a different choice this morning is not a theoretical abstraction. They're physically real, made of real matter, experiencing their life as completely and vividly as you're experiencing yours. The only thing that makes your branch feel like the real one is that you're in it. This is the level 3 multiverse in Tegmark's classification. And unlike the level 1 and level 2 multiverses, it doesn't require the universe to be infinite, or inflation to be eternal, or the string landscape to be real. It just requires that quantum mechanics is taken seriously, that the wave function is real, and the equations always hold, which is the most natural reading of the theory. Now, a lot of physicists are not comfortable with many worlds, not because of the math, but because of what it implies. It implies an almost incomprehensible multiplication of reality. If every quantum event branches the universe, and quantum events are happening all the time everywhere, then the number of branches is growing at a rate that defies any ordinary description. Every second, the number of branches of reality increases by something like 10 to the power of tens of trillions. In all of those branches, some version of you exists, having some version of an experience. Some physicists find this too extravagant. They prefer interpretations that don't multiply reality so aggressively. But here's the thing. The other interpretations of quantum mechanics all have their own problems. The Copenhagen interpretation says the wave function collapses when an observation is made, but doesn't define what counts as an observation or when exactly the collapse happens. The pilot wave interpretation works, but requires non-local hidden variables and doesn't extend naturally to relativistic physics. Various other interpretations have their own conceptual difficulties. Many worlds, whatever its metaphysical strangeness, has no collapse, no undefined terms, no special role for observers. It's just the equations applied consistently, which makes it, in a certain sense, the most economical interpretation, despite appearing to be the most extravagant. Whether many worlds is right is genuinely unknown, but if it is, the number of versions of you in existence right now is not some large finite number. It's something more like the cardinality of the continuum, the same infinity that describes the real numbers, rather than just the integers, not the infinity of distant space, but the infinity of branching moments. Here's something that doesn't get talked about enough. Every version of you in every branch of the quantum wave function, and every cosmic twin in every distant region of infinite space, experiences their life as the only one. They feel the same continuity you feel, the same sense of being a unique individual with a unique history, the same certainty that their choices are their own, that their experiences are singular, and from inside their branch, they're right. From their perspective, there's only one universe, one history, one them. They don't experience the branching, they experience only their branch. This is actually one of the most disorienting things about many worlds, and one of the things that makes it feel strange from a first-person perspective, even though it's perfectly coherent mathematically. Think about what happens when you flip a coin. In the many worlds picture, as soon as the coin is in the air, the wave function begins branching. In one branch it will land heads, in another it will land tails. You in the current moment are about to become two versions of yourself, one who sees heads and one who sees tails, both of whom will have memories of being you just now, before the flip, and neither of whom will know what the other sees. After the coin lands, neither version of you experiences anything strange. The version who sees heads just sees heads. The version who sees tails just sees tails. There's no awareness of the branching, no sense that reality just split. It just seems like the coin landed the way it landed. Now multiply that by every quantum event in every particle in your body and brain and environment happening constantly at a rate that would fill every hard drive ever built in a fraction of a microsecond every single moment of your life. That's the branching that's happening, and yet you experience none of it as branching. You experience it as a single, continuous, coherent reality. This is not surprising. The branches, by definition, don't interact after they diverge. Your branch is opaque to the others. The decoherence process, which is how physicists describe the way quantum superpositions lose their quantum character when they interact with large, complex environments, ensures that branches become independent of each other almost instantaneously. They can't be distinguished from within any branch. They can only be seen from outside from the perspective of the global wave function, which no observer inside any branch has access to. This means that the existence of all those other versions of you is permanently inaccessible to you. You will never experience being them. They will never experience being you. You cannot communicate with them, or even in principle know what's happening in their branches. In every practical sense, from the inside, you are the only version of yourself. But from the outside, from the perspective of the equations, all of you are real. This is one of those places where the physics and the lived experience point in opposite directions. Physics says all the branches are equally real. Experience says only one branch is real. Both are, in their own terms, correct. They're just using real to mean slightly different things. Here's where things get genuinely strange. And this is the part that most people have never heard of, even people who know about the multiverse. It's called the Boltzmann brain problem, and it's one of the most unsettling implications of the combination of a large or infinite universe and the laws of thermodynamics. Ludwig Boltzmann was a 19th century physicist who made fundamental contributions to our understanding of entropy, the thermodynamic quantity that describes disorder. His key insight was that entropy is related to probability. High entropy states are states that can be arranged in many ways. Low entropy states are states that can only be arranged in a few ways. The second law of thermodynamics, which says entropy always increases, can be understood statistically. It's not that disordered states are forced to arise, it's that they're overwhelmingly more likely than ordered ones, simply because there are so many more of them. A glass of water with ice in it is a low entropy state. The ice is a highly ordered arrangement of water molecules. As heat flows from the room into the ice melts, and the water molecules move from a more ordered to a less ordered arrangement. This happens because the disordered state is overwhelmingly more probable. If you waited long enough, by random thermal fluctuations, the ice could in principle reform. But the waiting time would be longer than the current age of the universe by an unimaginable factor. Here's the thing, in an infinite space and time, even incredibly improbable things happen. This is the same argument we made earlier about cosmic twins. If you wait long enough, or if there's enough space, random fluctuations will produce any configuration of matter you can name, including a human brain. A Boltzmann brain is a thought experiment. Suppose that in the far future, when the universe has expanded and cooled and stars have burned out, and most structure has dissolved into a low-density thermal equilibrium, random quantum and thermal fluctuations continue forever. In the vast stretches of this near-empty universe, occasionally, by pure chance, a fluctuation will produce an ordered structure, a complex one, and rarely, extremely rarely, one of these fluctuations will produce something as complex as a human brain, complete with fully formed memories and the experience of being a conscious person. This brain would spring into existence, have a subjective experience lasting perhaps a fraction of a second before dissolving back into the thermal sea, believing itself to be a real person with a real history. The memories it has are false, generated by the fluctuation rather than by actual experiences. But from the inside, it wouldn't know the difference. The troubling question that physicists have raised is this: in an infinite universe that persists long enough, how many Boltzmann brains are produced compared to ordinary evolved brains? If the answer is many more Boltzmann brains, then the most likely explanation for any particular conscious experience, including yours right now, would be that you're a Boltzmann brain. Your memories would be illusions. Your sense of a real history would be a random fluctuation. The universe you think you remember might not exist. This sounds like science fiction, but it's a real problem that cosmologists have spent serious effort on, because it's a genuine logical consequence of combining certain cosmological models with thermodynamics and the anthropic principle. If a cosmological model predicts that Boltzmann brains vastly outnumber ordinary evolved minds, that's actually an argument against the model, because we're fairly confident we're not Boltzmann brains. If we were, our memories of physics experiments and our experience of a consistent external world would be illusions, and the model couldn't actually be used to reason about reality. Most working physicists believe we're not Boltzmann brains, for several reasons. The most important is that our observed universe is in a particular low-entropy state that's consistent with a genuine early Big Bang, not with a random fluctuation. A Boltzmann brain fluctuation would produce only the brain and its memories, not an entire consistent low-entropy universe to go along with it. Since we observe a low-entropy universe, and since a random fluctuation would be much more likely to produce just a brain than a whole consistent universe, the fact that we're embedded in a consistent low-entropy universe is evidence that we're not Boltzmann brains. But the Boltzmann brain problem does illustrate something important. When you start combining infinite space, infinite time, and statistical mechanics, you get genuinely unexpected and hard to rule out possibilities. The possibility of cosmic twins and the Boltzmann brain problem both arise from the same basic observation. In a large enough universe, improbable things become inevitable. The question is always which improbable things, and that depends on the physics. What this all means is that the question of what exists and why is genuinely open in ways that go far beyond what most people realize. Now we're going to go one more level deeper. This is the one that leaves most people quiet for a while afterward. The level 1, 2 and 3 multiverses all share something in common. They're all physical. They're all part of a physical reality that has the same mathematical laws operating within it. Level 1 extends that reality further in space. Level 2 produces new regions with different physical constants. Level 3 branches it at every quantum event. But in all three cases, there's a physical world described by mathematics. The Level 4 multiverse, or the mathematical universe hypothesis proposed by Tegmark, goes further. It says that every mathematical structure that is consistent and self-defining corresponds to a real, physical existence. Not just our mathematical laws, not just nearby variations of our laws, but every possible mathematical structure, every possible set of equations, every possible formal system. If this is right, then our universe is not special in its mathematics. It's one of an infinite collection of mathematical structures, each of which is equally real in the sense that it has genuine existence. Some of those structures would be simple, just arithmetic, just basic geometry. Some would be enormously complex, with many dimensions, many particles, many forces. Some would contain structures complex enough to support what we call conscious observers. And among those, some would be this universe. This is the most radical version of the multiverse idea. It says that existence and mathematical description are the same thing. A mathematical structure that exists abstractly also exists physically. There's no separate physical substance added to the mathematics. The mathematics is all there is. If a self-consistent set of equations describes a universe with conscious observers, those observers are real. Why would anyone believe this? Not as a spiritual or aesthetic preference, but as a serious physical hypothesis. Here's the argument. When physicists describe our universe, they describe it with mathematics. They don't say there are particles and also there are equations that describe those particles. They say the equations are the deep description of reality. The more we learn about physics, the more reality looks like it's mathematical all the way down. There's no bedrock of physical stuff underneath the math. There's just the math. If that's true for our universe, why would it not be true for other mathematical structures? Why would our particular mathematical structure have the privilege of physical existence while others are just abstract objects? That asymmetry would need explaining. The mathematical universe hypothesis says there is no asymmetry. All consistent mathematical structures exist. Ours is just the one we find ourselves in, because it's one of the ones that supports conscious observers. This is actually a clean solution to one of the deepest puzzles in science. Why does the universe have the mathematical structure it has? The answer, in the mathematical universe hypothesis, is that it doesn't have to have any particular structure, it just has to have a structure. And we're in this one because this one allows us to exist. The implications of the level 4 multiverse for the idea of infinite versions of you are even more extreme than the earlier levels. In the mathematical universe hypothesis, every possible universe that contains a conscious being similar enough to you to count as you in some meaningful sense exists. Not just the ones with slightly different physical constants, or the ones where different quantum branches occurred, but universes with completely different physics that happen to support something analogous to human consciousness. Universes with 5 spatial dimensions and a different set of particles, if those universes can support something like minds. Universes with entirely different laws of causation, if those laws allow for self-referential complexity. In the level 4 multiverse, you is not just a particular arrangement of atoms in a particular universe, it's any mathematical structure complex enough to give rise to the pattern of information and processing that corresponds to your experience. And if existence and mathematical structure are the same thing, then all of those mathematical yous exist. This is the furthest edge of the idea, and it's genuinely unknown whether it's correct. Many physicists find it too speculative, too difficult to test, too reliant on philosophical assumptions that go beyond physics. Others find it the most natural completion of the direction physics has been going. The debate is real and it's ongoing. But the core of the claim, that mathematics and existence might be the same thing, is not obviously wrong. And if it's right, it changes not just what we think exists, but what we mean by existence itself. Let's come back down to Earth for a moment. In the many worlds interpretation, every time a quantum event could go one of several ways, all of the ways happen. Your choice, your decision, your action produces all possible outcomes in different branches. So what does it mean to choose? What does it mean to try to do something? If every possible outcome of your choice is real in some branch, does your choice matter? This is one of the most common objections to many worlds, and it's worth taking seriously. If every branch is real, and every branch contains a version of you experiencing its outcome, then what is the point of trying to make good choices? The good outcome happens in one branch, and the bad outcome happens in another, and both are real. Does your choice just determine which branch you end up in, not which branch exists? Here's how to think about this. Even in many worlds, choices have consequences. When you face a decision, the branches diverge based on what you decide. The branch in which you made a careful, thoughtful decision produces outcomes that reflect that care. The branch in which you made a careless decision produces outcomes that reflect that carelessness. You, as an agent making the decision, care about which branch you end up in because you'll be experiencing the consequences. It's like this. Imagine you're standing at the top of 2 different paths, and you know that one path leads to a pleasant destination and the other leads somewhere unpleasant. In many worlds, some version of you goes down each path, but that doesn't mean it doesn't matter which one you choose. You, right now at the decision point, are about to become the version who experiences one of those paths. You want to be the version on the good path. That desire is real and the choice is real. Probability in many worlds has a technical interpretation connected to the Born rule, which is the part of quantum mechanics that says how to calculate the probability of different outcomes. In many worlds, the Born rule becomes a statement about the weight of different branches in the wave function, what's sometimes called the measure of each branch. High probability branches have more measure, low probability branches have less. This determines how you should rationally act and what you should expect to experience. The details of how to derive the Born rule from many worlds is a deep technical question that physicists are still working on, but the basic point stands. Even if all outcomes occur, they don't all occur with equal weight, and rational behavior is to act as if you're maximizing expected outcomes, weighted by branch measure, which is the same thing you'd do if you believed in a single universe picture where probabilities are real. So the practical upshot is, your choices still matter. They determine which branch of reality you occupy, and that branch is the one you'll live in and experience. The fact that other versions of you live in other branches doesn't diminish the reality of your choice any more than the fact that other people live other lives diminishes the reality of your life. But here's the thing that does change. The choices that feel like failures, the paths not taken, the possibilities abandoned, in the many worlds picture, they're not lost. Some version of you took them. Some version of you is living the life you chose not to live. Some version of you is reading this right now from a completely different place in life than you are, and that version also feels like they're the one who made real choices. Whether this is comforting or disorienting depends on how you hold it. It can feel like it diminishes the significance of your particular path, since every path is taken, or it can feel like it validates all paths, since nothing is truly lost. Neither of those is more correct than the other. They're just different responses to the same fact. The question of free will connects naturally to all of this, and it's worth spending some time here because it's one of the places where the cosmological and the personal become genuinely entangled. The traditional problem of free will runs like this. If the universe is deterministic, if every event is the inevitable result of prior causes according to fixed physical laws, then your choices are not really free. They're the predetermined outcomes of physical processes in your brain, which were themselves predetermined by prior causes going back to the Big Bang. You feel like you're choosing, but the feeling is itself a predetermined event. Your sense of agency is an illusion. Quantum mechanics seemed at first to offer an escape, because quantum events are genuinely random, not just practically unpredictable, but fundamentally undetermined. Perhaps the randomness introduces a kind of freedom. The physical events in your brain are not predetermined by prior causes, because some of them are genuinely random. But random is not the same as free. If your choices are partly determined by random quantum events, that doesn't give you more agency. It just replaces deterministic unfreedom with random unfreedom. You're not freely choosing, you're just part of an unpredictable system. In the many worlds picture, the situation changes again. The wave function evolves deterministically. There's no collapse, no randomness in the fundamental dynamics. The branching appears random from the inside of any branch, but the global wave function is deterministic. So from the global perspective, everything is determined. From the local perspective, inside any branch, things look random. Neither perspective gives the traditional free will that most people intuitively believe in. But here's a different way to think about it. The question of free will might be asking the wrong question. The question, are my choices determined, presupposes that there's a fact about what your choice really is, independent of your perspective. But in a branching universe, there might not be such a fact. Your choice, as a physical event, produces all its possible outcomes. Which outcome you experience is a function of which branch you're in. But you are not a single entity traveling through a single fixed reality. You are a pattern that manifests in multiple branches, experiencing different outcomes in each. In this picture, the question of whether your choices are free might be less important than the question of what kind of entity you are. You are the kind of thing that makes choices, that reasons about options, that forms intentions and acts on them. Whether those choices are free in the strict philosophical sense might be beside the point. What matters is that reasoning and deliberation and intention are real processes that make a real difference to which outcomes occur, in which branches. Some philosophers call this compatibilism, the idea that free will, understood as the ability to act in accordance with your own reasoning and intentions without external compulsion, is compatible with determinism or quantum randomness. You're free not because you operate outside the laws of physics, but because the relevant description of your behavior is at the level of goals, intentions, and reasons, not at the level of elementary particles. In an infinite or many-branched universe, compatibilism feels increasingly natural. You are a reasoning, intending, acting entity embedded in a physical world. Your actions are determined by your reasoning, which is determined by physical processes, which are part of the wave function of the universe. But the level of description that captures what matters about you, the agent who deliberates and chooses, is a real level of description, even if it's not the most fundamental one. The infinite versions of you, near and far, don't diminish this. They're each also reasoning, intending, acting agents. Each of them has, from their own perspective, made genuinely effective choices that shaped their branch. None of them are more real than you, but none of them are more real than any other version either. You're all equally valid instances of the same kind of thing, each living fully and completely in your own corner of an unimaginably large reality. There's a classic thought experiment in philosophy of mind that becomes especially acute in this context: the teleporter problem. Imagine a device that works by scanning every atom in your body, recording their exact states and positions, then disassembling you and reassembling a perfect copy at the destination using fresh atoms. The copy is physically identical to you. It has all your memories, all your personality, all your continuity. Is the person who steps out of the teleporter at the destination you, or is it a copy? Did you die in the process? Most people have a strong intuition that this would be a bad way to travel, that the person who arrives is a copy, not a continuation. But when pressed to explain why, most people struggle. What exactly is lost in the disassembly? If the physical arrangement is perfectly reproduced, what's missing? Some people say consciousness. The original continuous stream of consciousness was interrupted. Even if the copy feels like a continuous stream of consciousness, the actual subjective continuity, the what it feels like to be you from the inside, was broken. The copy starts a new stream, the original ended. But here's the problem with this. Your sleep every night involves something very close to this interruption. Your consciousness goes through phases where it is either absent or radically discontinuous with your waking experience, and yet you wake up feeling like you. Most people don't feel that sleep is a form of death, even though it shares some features with the teleporter scenario. More fundamentally, what is this continuous stream of consciousness that we're trying to protect? Physically, it's a continuous process of electrochemical activity in your brain, but your brain's physical composition changes over time. Your neurons replace their molecular components. Your synaptic connections strengthen and weaken. The physical processes that constituted you 10 years ago are different from the ones that constitute you now. If you replace every part of a ship one plank at a time, is it still the same ship? That question, the ship of Theseus, is as old as Greek philosophy and still hasn't been resolved. In the context of infinite copies and many worlds, the teleporter problem becomes sharper. If there are already infinitely many physical copies of you in distant regions of space, each equally real, each equally continuous with the person who started the process, then in what sense are you unique? What does the continuity you feel actually track? One answer, increasingly popular among philosophers who take the physics seriously, is that personal identity is not a deep fact. It's a practical concept we use to organize our experience. It's useful in the same way that "this is my car" is useful even though no single molecule of the car is specially yours. The concept helps us navigate the world, but it doesn't correspond to a metaphysically special feature of reality. There is no soul substance that makes you you across time. There is just a pattern of physical processes with enough continuity for the concept of identity to be useful. In this picture, asking whether your cosmic twin is you is like asking whether the word bank in two different books is the same word. In one sense, yes, same letters, same sound, same meaning. In another sense, no, different physical instances of ink on paper. Which answer you give depends on what you need the concept for. Your cosmic twin is you in the sense that corresponds to physical identity. They're not you in the sense that corresponds to numerical, single instance identity. Both senses are legitimate, but neither is the uniquely correct one. Here is something that cosmologists and philosophers of physics wrestle with deeply, and it changes how we should think about the meaning of probability and existence in a multiverse. It's called the measure problem. In a finite universe with a finite number of outcomes, probability is well defined. You count the favorable outcomes, divide by the total outcomes, and you get a probability. A coin flip has two equally likely outcomes. A six-sided die has six equally likely faces. We can define and measure probability cleanly. In an infinite universe, things get more complicated. If everything that can happen does happen an infinite number of times, then for any two possible outcomes, both happen infinitely often, and comparing two infinities is not straightforward. Is the number of even integers greater than, less than, or equal to the number of all integers? In the most natural sense, half of all integers are even, so there should be half as many, but in another sense, both sets are countably infinite and have the same cardinality. The answer depends on how you define how many. The same problem applies in a multiverse. If there are infinitely many versions of you in infinitely many branches or regions, then how many of them made choice A versus choice B this morning? If we can't count them in a well-defined way, we can't compute probabilities in the usual sense. This is a genuine technical problem. It's not just philosophical hand-wringing. It affects whether predictions made by multiverse theories can be tested, even in principle. If you can't define what fraction of universe regions have property X, you can't predict how likely you are to find yourself in a region with property X. And if you can't make predictions, the theory becomes hard to evaluate scientifically. Various approaches have been proposed. One is to use a measure on the infinite set of branches or regions, a mathematical tool from measure theory that assigns weights to subsets in a consistent way. Different choices of measure give different probabilities, which is itself a problem. Another approach is to use some physical process to define a natural measure, such as counting by volume of space or by number of quantum events. None of these approaches is fully satisfying yet. The measure problem is one of the central open questions in the physics of the multiverse. It's part of why some physicists are skeptical of multiverse ideas, even if they accept the basic physics of inflation or quantum mechanics. Without a well-defined measure, the multiverse makes imprecise predictions, and imprecise predictions are hard to confirm or rule out. But here's the thing. The measure problem doesn't mean the multiverse doesn't exist. It means we don't yet have the mathematical tools to fully reason about it. This is not the first time in physics that a correct idea outran our ability to calculate with it. Quantum mechanics itself took decades to interpret properly, and we're still arguing about it. General relativity predicted black holes decades before anyone thought they could actually exist. The measure problem is a technical obstacle, not a philosophical refutation. And in the meantime, the qualitative picture that in an infinite universe with uniform physics, every possible arrangement of matter that can occur will occur remains a well-founded consequence of the best physical models we have. Let's be honest about what we know and don't know, because this is important. We've covered a lot of ground, and some of it is much more speculative than other parts. Let me separate these clearly. What we know with high confidence: the universe is about 13.8 billion years old. The observable universe is about 93 billion light-years across. The universe is geometrically flat to within our current measurement precision of about 4.4%. The early universe underwent a period of extremely rapid expansion that left specific signatures in the cosmic microwave background. Quantum mechanics is correct to extraordinary precision. Quantum systems genuinely exist in superpositions before measurement. What we have strong reasons to believe but cannot directly verify: inflation is eternal, in the sense that once it starts, it continues generating new pocket universes. The universe extends far beyond our observable horizon. The cosmological principle holds beyond our observable horizon. What is a reasonable hypothesis with theoretical support but less observational backing? The string landscape of multiple possible vacuum states, the many-worlds interpretation of quantum mechanics as the correct interpretation, rather than just one among several. What is highly speculative but logically coherent? The mathematical universe hypothesis. The cosmic twins argument is most solid in the level 1 case, which rests only on the universe being infinite and the cosmological principle holding. If you accept those two premises, the mathematics is straightforward. The level 2 case adds the requirement that inflation is eternal, which is a prediction of most inflationary models, but not directly verified. The level 3 case requires many worlds to be the correct interpretation of quantum mechanics, which is a serious scientific hypothesis, but not settled science. The level 4 case is the most speculative. So the honest answer to "are there copies of you in the universe?" is probably yes if the universe is infinite and the cosmological principle holds, which our best current physics suggests. Possibly many more if eternal inflation and the string landscape are real. An enormous and possibly infinite number if many worlds is correct, and an infinite number in a much more exotic sense if the mathematical universe hypothesis is correct. The minimum version of this idea requires only the most basic and well-supported physics, and that minimum version is already quite substantial. It would be wrong to leave you with the impression that this is all settled or universally accepted. Physicists genuinely disagree about these ideas, and some of the most respected scientists in the world are skeptical for reasons worth understanding. One concern is testability. Science progresses by making predictions and testing them. A theory that predicts something you can never check is, in a sense, not a scientific theory in the usual meaning. The cosmic twins in distant regions of an infinite universe or in other pocket universes of an inflationary multiverse can never be observed from here. No signal from those regions can reach us, so the prediction of their existence can't be directly confirmed. This bothers some scientists deeply. They argue that a theory whose central predictions are in principle unobservable is metaphysics, not physics, regardless of how mathematically rigorous it is. Others argue that this is too strict a criterion for what counts as science. A theory can be well evidenced and explanatorily powerful, even if not all its predictions are directly testable. The existence of the interior of a black hole is also in principle unobservable from outside, but most physicists believe the interior exists and reason about it. Another concern is complexity. The many worlds picture requires all those branches to be equally real. The inflationary multiverse requires an ongoing sea of inflation generating new universes constantly. The mathematical multiverse requires all consistent mathematical structures to exist. From a principle of parsimony, Occam's razor, the simplest adequate theory is preferred, and some physicists find a single universe simpler than infinitely many. Others argue the opposite, that it takes more assumptions to make the universe uniquely exist than to let it exist as part of a larger ensemble. Imposing the constraint "only this universe exists" requires an explanation for why all possible universes exist, requires no such arbitrary selection. There's also the question of what counts as parsimonious in this context. Is a theory simpler because it postulates fewer physical entities, or because it uses fewer laws and principles? A single universe is simpler in the entity count sense, but the laws that make it uniquely that one universe might be vastly more complex than the law that says all possible universes exist. These two measures of simplicity conflict. George Ellis and Joe Silk, two prominent cosmologists, argued in Nature in 2014 that the scientific method itself is at stake when physicists argue for untestable multiverse theories. They worry that accepting theories on theoretical grounds alone, without empirical confirmation, sets a dangerous precedent. Meanwhile, Max Tegmark, David Deutsch, and Brian Greene are among the leading physicists who take multiverse ideas seriously as scientific proposals. This is a genuine, unresolved debate among serious people. The fact that it's happening at the highest levels of physics is itself worth noting. These ideas are not fringe. They're central to the most active areas of theoretical physics. The debate is about how to interpret and constrain the ideas, not about whether they're worth taking seriously. We've been talking about copies of you, many versions of you, versions identical to you in every physical detail, versions that differ from you in one choice or a million choices, versions in other quantum branches, versions in other regions of infinite space, versions in other pocket universes with different physics, versions in other mathematical structures. But underneath all of this is a question that's hard to state clearly because it touches something we usually leave unexamined. The question is, what are you? Not who are you, what? Most of us carry around an implicit answer to this question. You are your memories, your personality, your continuous experience, your sense of self. You are the particular thing that woke up in your body this morning and will go to sleep tonight and wake up again tomorrow in what feels like a continuous thread. But physics suggests that this implicit answer is at best a useful approximation. The you that is described in physics is a pattern of information encoded in matter, a highly specific, temporary, exquisitely organized configuration of atoms and energy that processes information, generates predictions about its environment, models itself and the world around it, and experiences something. Whatever that something is, we still don't understand consciousness well enough to say more. This pattern is not unique. It can in principle be instantiated in other places. It can branch. It can persist in different forms. The continuity you feel is real, from your perspective inside the pattern, but it's not a fundamental feature of the universe that selects you out as the special one. The universe, if it's large enough, is full of this pattern, instantiated in many places and in many states. What does this mean for how we should live? That's genuinely up to you. Philosophy doesn't give a single answer to what the existence of cosmic twins implies for how to think about your life. Some people find it reduces the weight of individual choices, since every choice gets made in some branch. Others find it increases the responsibility of each moment, since this branch, this version of you, is the one you're actually living. Some people find it comforting, since nothing is entirely lost if every possibility is realized somewhere. Others find it isolating, since all those other versions of you are completely beyond reach. What the physics doesn't tell us is that the life you're living doesn't matter. In fact, from inside your branch, your life is the entirety of reality as you experience it. And the structure of consciousness, the way it integrates experience, the way it connects past to present to future, is real and functioning and meaningful regardless of how many other instances of similar consciousness exist elsewhere. You are real. Your choices are real. Your experiences are real. The fact that you might have cosmic twins doesn't change any of that. It just changes the backdrop. It changes how large and how strange the stage is on which your particular experience is occurring. Here is something to hold on to amid all this speculation. Multiverse ideas, while difficult to test directly, are not entirely without observable consequences. There are things we could potentially observe that would be evidence for or against some versions of the multiverse. One example comes from the cosmic microwave background, the radiation left over from the early universe. If our bubble universe, the pocket of inflation we inhabit, has collided with another bubble universe in the relatively recent cosmic past, that collision might have left a signature in the cosmic microwave background, a ring-like pattern, or a disk of different temperature or polarization. Cosmologists have searched for such signatures. Some claim to have found hints, though nothing convincing enough to stand up to scrutiny. The search continues. Another potential test comes from fine-tuning arguments and the anthropic principle. If we understand the string landscape well enough to predict the probability distribution of different physical constants in different pocket universes, we can ask whether the constants we observe are typical of the subset of universes compatible with observers like us. If our constants are wildly atypical, even within the observer-compatible subset, that would be evidence against the landscape picture. If they're typical, that's consistent with it. We're far from having the landscape theory well enough understood to do this calculation rigorously, but it's a direction in which the science could progress. For the many worlds interpretation, the situation is different. Many worlds makes exactly the same predictions as other interpretations of quantum mechanics for any experiment you can perform within a single branch. That's both its strength and its weakness as a scientific proposal. Its strength because all quantum experiments have confirmed quantum mechanics, and many worlds is a valid interpretation of that confirmed theory. Its weakness because there's currently no experiment that can distinguish between many worlds and other interpretations. Some physicists think this might change. There are theoretical proposals for experiments that could in principle distinguish between interpretations, though they would require a level of control over quantum systems far beyond what we currently have. If those experiments become possible in the future, we might be able to test whether the wave function truly never collapses. The mathematical universe hypothesis is the hardest to test, essentially by its own logic. If all mathematical structures are real, then the specific mathematics of our universe is just a selection criterion, not a prediction. This makes it very difficult to say what observations would confirm or rule out the level 4 multiverse. But science has made progress on seemingly intractable questions before. 50 years ago, dark matter and dark energy seemed like they'd be forever out of reach of direct confirmation. We still haven't confirmed them directly, but we've built a remarkably consistent picture that fits dozens of independent observations. The multiverse might be similar, not directly observable, but increasingly constrained by indirect evidence until the picture becomes convincingly coherent. Or the evidence might point the other way, and we'll conclude that the universe is finite after all, and the cosmic twins are a consequence of a model that's wrong. Either outcome would be remarkable. Either outcome would tell us something deep about the structure of reality. Let's bring this all the way home. We've been talking about you in the abstract, about the theoretical person whose pattern of matter is replicated in distant regions of an infinite universe, who branches at every quantum event, who might exist as a necessary instance in every mathematical structure, complex enough to support your pattern. But let's think about what this means for the specific you sitting here right now, listening or reading this, thinking these thoughts. You are, at this moment, a particular configuration of matter processing information about the universe. Some of the information you're processing is coming from this script, which tells you about the possibility that you exist in many copies. This specific process, this exact moment of reading or listening, is itself an event that in the multiverse picture is occurring in infinitely many branches and infinitely many distant regions. Right now, there is a version of you in another branch who paused this to get a glass of water and is just coming back. There is a version of you who never started this at all and is doing something else. There is a version of you who heard all of this and found it clarifying rather than disorienting. There is a version of you who is explaining this to someone else right now. And there is a version of you who is having the same thought you're having at this moment, which is the strange looping awareness that comes from thinking about infinitely many versions of yourself, all having the same thoughts simultaneously, including the version who is thinking that the loop itself is interesting, including the version who finds the loop a bit much and is moving on. All of those are real in the sense that physics tells us real means, and you, the one here, are real in exactly the same sense. No more, no less. You are not the original, because there's no original. You're not a copy, because copy implies an original. You're an instance, one of infinitely many instances of a pattern, each one fully real, fully complete, fully you. This is not a new idea dressed up in physics. It's a genuinely old human intuition, that the self is not what it seems, that the sense of being uniquely you is a kind of narrative construction over a more fluid underlying reality, that what persists through time is a pattern, not a substance. Philosophers, meditators, and poets have touched this intuition through other routes. Physics just approaches it from the direction of equations and predictions. What's new is that physics gives it a specific mechanism, not vague spiritual multiplicity, but precise physical mathematics. Not a metaphor for impermanence, but an actual, calculable consequence of cosmology and quantum mechanics. The familiar intuition that you are both special and not so special, that you are continuous and also always changing, that you are singular and also part of something much larger, turns out to have a mathematically rigorous version buried in the foundations of modern physics. This might be the most important section, because the possibility of infinite versions of you, compelling and well-grounded as it is in current physics, rests on assumptions that might be wrong, and being clear about what we don't know is not a sign of weakness in the science. It's one of the most important features of how science actually works. We don't know if the universe is infinite. We know it's flat to within our measurement precision, but a slightly curved universe that's finite could be so large that our measurements can't detect the curvature. Such a universe would be enormously large but not infinite, and in a merely enormous but finite universe, the cosmic twins argument works only if the universe is large enough. If it's large but finite, there might be 0 copies of you, or many, depending on the size. We don't know if inflation is eternal. Eternal inflation is a robust prediction of many inflationary models, but the details of the inflaton field are unknown and different models give different predictions. Some inflationary scenarios don't produce eternal inflation. Without eternal inflation, the universe might be large but not a sea of pocket universes. We don't know if the string landscape is real. String theory is mathematically rich and has properties that make many physicists believe it's on the right track. But it hasn't produced confirmed predictions in the way the standard model of particle physics has. The landscape of vacua might be a real feature of nature, or might be an artifact of how string theory is currently formulated. We don't know if many worlds is the correct interpretation of quantum mechanics. It's a natural reading of the formalism, and many physicists find it compelling. But natural and correct are not the same thing. Other interpretations remain viable, and distinguishing between them may require experimental capabilities we don't currently have. We don't know if consciousness, identity, and personal experience are the kinds of things that can be replicated or branched in the ways the multiverse picture suggests. If there's something about consciousness that isn't captured by the physical pattern of a brain, if there's something more to subjective experience than the physical arrangement and processing of matter, then the claim that another you exists somewhere might be more complicated than it sounds. The hard problem of consciousness, the question of why there's something it feels like to be you, remains genuinely unsolved. Each of these unknowns is a real limit on our current knowledge. The multiverse is not a settled fact. It's the best current picture given the best current physics, and that picture is compelling, but science is a process of continually refining the picture, and future discoveries could shift this significantly. What we know for certain is that the universe is enormously larger and stranger than ordinary experience would suggest. That our place in it is not central in any physical sense, that the laws of physics don't seem to have been set up specifically for us, and that the mathematics of an infinite or near-infinite universe has implications that are genuinely surprising and genuinely unsettling and genuinely worth sitting with. We've been in the cosmology for a while. Let's be concrete about what this means for actual human life. Not abstractly, concretely. If there are infinitely many versions of you, then every worst version of you is also real. Every version of you who made the worst possible choices in every situation, who hurt the people you care about most, who lived in a way you'd be ashamed of, is out there, equally real, equally physical, equally conscious. They feel bad about their life the same way you'd feel bad about it. They're real people having real experiences. And every best version of you is also real. Every version who rose to every challenge, who was patient when you were impatient, who said the right thing when you said the wrong thing, who made the choice you wish you'd made, they're out there too. They're real. They're you. This is not a reason to feel relieved that the good versions exist, or despairing that the bad versions exist. It's more subtle than that. Because you, the one making choices right now, are not guaranteed to be either the best or the worst version. You're just the version in this branch. And the version in this branch can still make better or worse choices from here. Here's the thing about the infinite versions. They don't help each other. They can't communicate. They can't share resources or advice or comfort. The version of you who figured everything out perfectly can't transfer that to the version still struggling. Each version lives in isolation from all the others, making their way in their branch with only what they have. The existence of better versions of you doesn't make your version's situation easier, and the existence of worse versions of you doesn't make your situation more forgivable. All of which means that the existence of infinite versions of you doesn't change the basic situation of the version you're in. You still have to make choices. You still have to live with them. You still have to navigate a complex world with incomplete information and finite time and real consequences. The cosmic scale of the multiverse doesn't dissolve any of that. It just changes the context in which it happens. And there's something oddly human about that. The universe is vast beyond comprehension. Your individual existence is a tiny flicker in it. Other versions of you exist in numbers that can't be meaningfully stated, and none of that changes the immediate reality of whatever you're dealing with today. That gap between the cosmic and the personal is something humans have always lived in. The multiverse just makes the cosmic end of it even more extreme. Here's something worth noting. The conclusions that physics is now groping toward about the nature of the self, its fluidity, its lack of a fixed essential core, its embeddedness in a larger physical reality, are conclusions that certain traditions of philosophy and contemplative practice arrived at through other routes, centuries or millennia before modern cosmology. Buddhist philosophy, for example, has long held that the self is not a fixed, essential entity but a process, a temporary pattern of mental and physical events that gives rise to the experience of selfhood without there being a self-substance underneath it. The concept of anatta, often translated as non-self or not self, doesn't say that you don't exist. It says that the self you think you are, the fixed, continuous, essential you, doesn't quite exist in the way you think it does. What exists is a process, a pattern, an ongoing event. This maps remarkably well onto what physics suggests. The you that physics describes is a pattern of matter and information, not a substance. It's a process that persists through time by maintaining its pattern, not by carrying the same atoms around with it. There's no soul substance that makes you you in addition to the physical pattern. There's just the pattern. Stoic philosophy, coming from a different direction, arrived at something related. The Stoics argued that attachment to the idea of a unique, continuous, essential self is a source of suffering because that self is fragile, temporary, and dependent on circumstances beyond your control. The wise response is to identify less with the particular configuration, the specific body and specific history, and more with the capacity for reason and virtue that any configuration of you could manifest. Again, this maps. If infinitely many configurations of you exist, each equally real, then identifying too strongly with this particular configuration is a form of category error. You're not uniquely this one instance. You're the kind of thing that this kind of pattern gives rise to. Anywhere the pattern occurs, that's a real instance of what you are. And what you are, as the Stoics might say, is less about the specific matter and more about the character and choices that the matter enacts. I'm not saying physics has confirmed Buddhist or Stoic philosophy. These traditions arrived at their insights through very different methods, and physics is not their successor or validator. But the convergence is interesting. It suggests that the insight that selfhood is more fluid and relational and constructed than it seems is not just a product of any one method of investigation. It's a truth that multiple routes of honest inquiry tend to arrive at from different directions. There's comfort in that, maybe, or at least company. Across cultures and centuries and methods of inquiry, thoughtful people have come to similar conclusions about the nature of the self. Physics is the latest addition to that conversation, and physics brings precision and testability that the earlier methods lacked, but it's building on a very old intuition. There's a self-referential quality to this conversation that's worth making explicit. You are a conscious entity learning about the possibility that many versions of you exist. That learning, that process of updating your model of the world to include this information, is itself a physical process. It's changing the state of your brain, which means that right now, you're becoming a different pattern from the one you were at the beginning of this. The you who started reading this and the you who finishes it are in a slightly but genuinely different state. Your neural connections have been strengthened or weakened in ways that reflect this new information. Your model of the universe and your place in it has updated, and because these changes are real and physical, the version of you who exists at the end of this is, in a precise sense, different from the one who started. And in the many worlds picture, as you processed each sentence, each idea, each moment of understanding or confusion, the quantum events involved in your brain's processing branched the wave function. There's a version of you who found this more clarifying than the one you're experiencing now. A version who found it less convincing. A version whose brain processed these ideas in ways that changed them more, or less, or differently. All of those versions now carry a version of this knowledge in them. Some carry it lightly, having skimmed. Some carry it deeply, having thought carefully about every section. Some will pass it on to other people, and some won't. The universe of minds that now contains some version of these ideas is larger than it was before this video or this reading existed. That's not unique to this content. It's what all communication does. Every piece of information that passes from one mind to another is a physical process that changes both minds and, through them, the world. Every book, every conversation, every lecture, every argument is a reconfiguration of the matter in brains, spreading patterns through the network of human consciousness. If the multiverse is real, then for every version of you who encountered these ideas, there's a version who went in a different direction and doesn't know any of this, and there's a version who knew it already and is now thinking about it differently because of how this particular framing put it. All of those versions are real. All of those versions of the knowledge and the absence of the knowledge and the different versions of the knowledge are being instantiated in real brains made of real matter, in real branches of the wave function. You are part of this larger system, whether you think of yourself that way or not. Your mind, your particular configuration of conscious experience and knowledge and memory, is a node in a vast network of minds, and that network extends in the multiverse picture, not just across the human population of Earth, but across all the instances of all the people who have ever thought, in all the branches and regions where they exist. Before we get to the question of whether any of this is terrifying, let's take a moment with something that might help. Because the idea that we are not unique, that our matter and our patterns are not singular, is not actually new, it's just new at this scale. Look at the stars. For most of human history, people believed the stars were fixed lights in a dome above the Earth, essentially decorations for the human drama below. We now know they're suns, enormous balls of burning plasma, each one its own version of the thing that warms our world. Many of them larger than ours, many of them smaller, many surrounded by their own planets, their own orbits, their own potential chemistries. The sun was once thought to be unique, irreplaceable, the very center of the cosmic order in early heliocentric models. Then we found out it's one of about 300 billion stars in the Milky Way alone. About 300 billion. If you counted one star per second, you'd need around 9,500 years to count all the stars in our galaxy. Then we found out that the Milky Way is one of perhaps 2 trillion galaxies in the observable universe. The Sun is one of roughly 200 sextillion stars in the observable universe, a 2 followed by 23 zeros. Did that make the Sun less important to us? Did the warmth of a summer afternoon get colder? Did sunrise become less beautiful once we knew it was one of trillions of similar events happening every moment across the galaxy? For most people, no. The abundance didn't diminish the experience. It changed the context and perhaps deepened it. Knowing what a star actually is makes the sunrise more interesting, not less. The same thing happened with Earth. People once assumed that Earth was the only planet. Then we found the other planets in our solar system. Then we found that nearly every star has planets. We now estimate there might be more planets in the observable universe than there are grains of sand on all of Earth's beaches combined. Earth is one of that number, and yet it is still, from where you're standing, the world. The pattern keeps repeating. We discover that what we thought was unique is abundant, and then we adjust, and then usually we find something new to appreciate about the abundant thing that we couldn't see when we thought it was singular. The you in the mirror was always abundant in this way. Every human is a temporary configuration of atoms that have existed since before the solar system formed. The carbon in your body was forged in the core of a star that died before our sun was born. The iron in your blood was made in a supernova so energetic that for a few days it outshone the entire galaxy it lived in. You were made of stellar debris, organized into a pattern complex enough to look at the stars and recognize them as cousins. The multiverse just extends this observation further. You are not uniquely organized, you are prolifically organized. Your pattern is one that the universe, given the right conditions, produces repeatedly. That's not a diminishment, that's a feature of what kind of thing you are. The title of this exploration used the word terrifying, and it's worth asking honestly, is this terrifying? When you sit with all of it, the infinite copies, the branching, the mathematical multiverse, the possibility that your uniqueness is a kind of practical fiction rather than a deep feature of reality, what is the actual emotional texture of it? For some people, it genuinely is unsettling. The loss of uniqueness feels like a loss of meaning. If infinitely many versions of you exist, then nothing you do is truly yours alone. If the good things you do are done by infinitely many of you, they're not special. If the bad things you do are also done by infinitely many of you, they're not your responsibility. The whole structure of moral self-assessment seems to require a singular you who is truly the agent of your actions. But here's something interesting. Most of the things that give life meaning don't require cosmic uniqueness. The love between two people is real and specific, even if identical configurations of those people exist elsewhere. The satisfaction of solving a difficult problem, the beauty of a piece of music, the warmth of a shared meal, none of these require that no one else is having the same experience simultaneously. In fact, we know right now that many people are having the same or similar experiences, and it doesn't diminish the experiences we have. The person sitting in a different city reading the same book you're reading right now is having an experience similar enough to yours that you'd recognize it as a cousin of your experience. That doesn't make your reading of the book less real or less valuable. It just means the book is doing something for multiple people simultaneously. If infinitely many cosmic twins are reading the same book in infinitely distant regions, it's the same situation at a vaster scale. The experience is still yours, still real, still exactly as vivid. For others, the multiverse picture is genuinely comforting. The idea that no version of you is lost entirely, that every path you didn't take is being lived by some version of you, that the possibilities aren't truly foreclosed but just experienced elsewhere, has a certain warmth to it. The person you might have been is real. They're out there. They made it. They're living that version of your life fully. Whether that's comforting depends on whether you feel attached to the specific path you've taken or attached to the possibilities you've left behind. Both responses are human and valid. What I notice, thinking about this at the level of lived experience rather than abstract philosophy, is that the multiverse picture doesn't really change the texture of being alive. You still wake up as you still have the relationships you have and the work you have and the ordinary weight of ordinary days. The universe's strangeness exists at a scale that ordinary life operates mostly independently of. The fact that there are other yous out there doesn't change what you need to do today. It just changes the frame in which you understand what you means. And that frame change can be valuable, not because it solves any practical problem, but because the way you understand yourself and your place in reality shapes how you engage with existence. If you understand yourself as the one and only unique instance of your particular combination of traits and experiences, you might carry a certain kind of weight, the weight of being irreplaceable, the weight of choices that can never be undone. If you understand yourself as one instance of a pattern that exists across a vast landscape of possibility, the weight changes. Not lighter, not heavier, just differently distributed. We've covered the cosmological grounds for cosmic twins. We've covered the quantum mechanical grounds. We've covered the philosophical implications. But there's one question underneath all of this that we haven't really answered, and it might be the deepest one. Why is there something rather than nothing? Everything we've talked about presupposes that the universe exists, that physics is real, that there are atoms and energy in quantum fields and the laws that govern them. But why? Why is there a universe at all? Why does anything exist? Why isn't there just nothing? This question predates science. Philosophers have asked it for as long as philosophy has existed. Leibniz called it the fundamental question of metaphysics, and it's remained stubbornly unanswered. The mathematical universe hypothesis offers one response. If all mathematical structures exist, then something is inevitable, because mathematical structures exist necessarily. A mathematical truth is true regardless of whether a physical universe exists to instantiate it. 2 + 2 = 4 whether or not atoms exist. The Pythagorean theorem is true whether or not there's any physical space. If existence and mathematical structure are the same thing, then existence is as necessary as mathematical truth, and the question, why is there something, has the same answer as why are mathematical truths true, because that's what mathematical truth means. This doesn't fully satisfy, because you can still ask, why does the concept of mathematical truth exist? Why is there logic rather than no logic? What makes the mathematical universe hypothesis itself true? These questions spiral into an infinite regress that no current framework fully resolves. Physicist Lawrence Krauss has argued that the universe could have arisen from nothing through quantum mechanical processes, but the kind of nothing he's talking about is not truly nothing. It's a quantum vacuum, which has properties, which has laws, which has energy fluctuations. It's not the absence of everything. It's the absence of matter and radiation against a background of quantum fields. Why there are quantum fields and why they have the properties they do is still an open question. So we don't know why anything exists. We have increasingly detailed descriptions of how things that exist behave. We have compelling models of how the universe evolved from its initial state. We have plausible hypotheses about how it came to have the initial state it had. But the question of why there's a something rather than a nothing remains genuinely open. And here's the strange thing about that question, in the context of everything we've discussed. If the universe contains infinitely many versions of you, if the multiverse is real and the mathematical universe hypothesis is right, then the question isn't just why there's something, it's why there's everything. Because a mathematical universe contains not just this particular something, but all possible somethings simultaneously. Why is there something rather than nothing becomes why is there everything rather than nothing? And that question has a different flavor. It's less like asking why a specific coin landed heads, and more like asking why probability exists. We don't have an answer to that, but knowing that's the right question to ask is something. Here's something that doesn't get enough attention in conversations about the multiverse: time. We've been thinking mostly about the spatial distribution of cosmic twins, about how far away another you might be in an infinite universe. But time matters too, and the timescales of cosmology are so extreme that they change the picture in important ways. The universe is about 13.8 billion years old. 1 billion years is so long that it's nearly impossible to feel. Every second that has passed since you were born, every minute of sleep and work and conversation and waiting and thinking is a tiny fragment of a single year. 1 billion of those years is 1,000 million of them. If the entire history of Earth were compressed into a single 24-hour day, modern humans would appear in the last 2 seconds before midnight. And the universe will likely continue for far longer than it's been running. Current estimates for the lifespan of the universe before all stars have burned out put it at about 100 trillion years. That's about 7,000 times longer than the universe has already existed. 100 trillion years from now, the last red dwarf stars will be guttering out. After that, there's the degenerate era, when white dwarf remnants cool slowly over trillions more years. Then the black hole era, when black holes dominate and slowly evaporate over timescales that make 1 trillion years look like a morning. Hawking radiation will evaporate even the largest supermassive black holes over something like 10 to the power of 100 years. That number, 10 to the 100th power, is called a googol. If you counted 1 atom per second since the Big Bang, you'd have counted about 400 septillion atoms, which is roughly 1 trillion times less than a googol. What happens after that? We don't know. But if the universe persists indefinitely, if dark energy continues to drive expansion, but doesn't eventually reverse or change character, then what's left is an increasingly cold, dark, expanding void. And in that void, over truly astronomical timescales, random quantum fluctuations continue, including the kinds of fluctuations we talked about when we discussed Boltzmann brains. But there's another dimension to time in the multiverse picture. In eternal inflation, new pocket universes are constantly being generated. The process has no known end. Pocket universes with physics like ours continue to form, continue to develop galaxies and stars and planets and the conditions for life long after our own pocket universe has grown cold and dark. In fact, since inflation has been going on for as long as it's been going on, and since it generates new pockets constantly, the number of pocket universes that will ever exist, if eternal inflation is real, is not a number at all. It's a diverging infinity. More pockets are added every moment, forever, each with its own Big Bang, its own history of stars and planets, its own versions of you. Time, then, is not just a direction from past to future in our universe. In the full multiverse picture, time might be the medium through which new universes are constantly generated, each one starting its own clock, each one running its own history. Our universe's clock is about 13.8 billion years in. Somewhere out there, another pocket universe's clock started 1 second ago. Another started before our universe began. Each of those universes has its own relationship to time, its own sequence of events, its own moment that corresponds to right now, for whatever forms of consciousness it contains. The multiplicity of yous is not just a spatial fact, it's a temporal one. The pattern that gives rise to you is not just widespread through space, it's being generated again and again through the ongoing process of cosmic creation, in new universes, at new moments, in new histories. You are not just one instance in a vast space, you are one moment in a vast, ongoing generation of reality. That might be the part that stays with you longest. That the creation of new universes, new histories, new versions of everything that exists might not be something that happened once 13.8 billion years ago and stopped. It might be something that's happening right now and will continue to happen, producing new versions of the conditions for life, and eventually new versions of the specific patterns that make consciousness possible indefinitely. In which case, the universe is not growing old, it's growing. The physics of the multiverse is not finished. It's in active development in several directions, and the next few decades could change the picture significantly in either direction. On the observational side, the next generation of cosmic microwave background experiments will map the radiation with higher precision than ever before. The CMB-S4 experiment and the Simons Observatory are planned to map the polarization of the CMB with a sensitivity that could detect gravitational waves from the inflationary period. If those gravitational waves have the right properties, they could confirm specific models of inflation and give us better constraints on what happened in the very early universe, including whether inflation is the eternal kind. Space-based gravitational wave detectors, particularly the planned LISA mission, which should launch in the 2030s, will observe gravitational waves from sources across cosmic history. These observations could reveal things about the very early universe that are currently hidden from light-based telescopes. The universe was opaque to light for its first 380,000 years, but it was never opaque to gravitational waves. If we can detect gravitational waves from the inflationary epoch, we can look back further than any telescope has ever seen. On the theoretical side, quantum gravity, the marriage of quantum mechanics and general relativity, remains one of the central unsolved problems in physics. String theory is one approach, loop quantum gravity is another. Several others are being actively developed. A successful theory of quantum gravity might give us a much clearer picture of what happened at the Big Bang and before, what determines the initial conditions of the universe, and whether those initial conditions are part of a larger structure. Progress in our understanding of complexity and consciousness might also be relevant. If we develop a much clearer scientific account of what consciousness is and what physical conditions are necessary and sufficient for it, we'd be better equipped to reason about whether the many versions of you in the multiverse would actually be conscious. This connects to what philosophers call the hard problem of consciousness, and it's one of the most active and contested areas of both philosophy and neuroscience. The development of quantum computers, which are now becoming real and practical rather than purely theoretical, might also contribute. Quantum computers work by harnessing quantum superposition and entanglement to perform calculations. If many worlds is real, then quantum computers are in some sense performing computations across multiple branches simultaneously. The fact that they work and the ways they work might provide indirect evidence about the structure of the quantum world and the plausibility of the many branches picture. None of these developments is guaranteed to resolve the multiverse question definitively. These are hard problems and progress is slow, but the direction of travel is toward better tools, better theories, and better constraints on these ideas. We're not standing still. The questions we're asking are hard, but they're not being avoided. Let's slow down and let everything settle. We started tonight with the assumption that most people carry around, that there's one universe, one history, one you, and we've traced, step by step, why the best current physics suggests this assumption is almost certainly wrong. The universe, based on its observed geometry, is probably either infinite or so large that the difference is practically irrelevant. In an infinite universe with uniform physics, your particular arrangement of matter is necessarily replicated, not once but infinitely many times, at distances so enormous they can't be meaningfully expressed in ordinary language, but which are nonetheless finite and physically real. The period of rapid expansion in the early universe, inflation, was almost certainly an eternal process that generates new pocket universes constantly, each potentially with its own physical laws, each the size of a full universe in its own right. Among those pockets, the ones compatible with physics like ours would contain their own infinite spaces, their own instances of everything that can arise from those physics. Quantum mechanics, the deepest theory of physical reality we have, predicts that every quantum event branches the wave function of the universe, producing all possible outcomes, each in its own real and physical branch. The number of branches increases at a rate beyond any human comprehension, every moment, everywhere, and you are in every one of them, in different states, having different experiences. If the mathematical universe hypothesis is right, then every consistent mathematical structure exists, and among the many mathematical structures complex enough to support consciousness, there are infinitely many that contain something that is, in the relevant sense, you. And beneath all of this is the realization that the you, who all of this is replicated, branched, and instantiated, is not a sole substance or a fixed essential identity, but a pattern, a specific, complex, beautiful, temporary pattern of matter and information that processes the world and generates the experience of being you. A pattern that can in principle exist in many places, in many forms, across a reality that is far larger and stranger than the room you're in right now. This doesn't make you less real, it makes reality larger. It doesn't make your life less significant, it changes what significance means and where it lives. It doesn't answer the deepest questions, why anything exists, what consciousness is, what the ultimate nature of reality is, but it reframes them. It puts them in a context that no previous generation of human beings had access to. You are standing at a moment in history when the conversation between physics and philosophy and human self-understanding is at one of its most intense points. The questions being raised now about the structure of reality, about the nature of the self, about the scope and boundaries of existence, are questions that will shape how human beings understand themselves for generations. You're part of that conversation. Just by thinking about these ideas, you are contributing to the living process by which human understanding grows. And there are infinitely many versions of you, right now, having this same thought, each of them feeling, as you feel, that they are the one having it. We've come a long way from the opening question. We started with the simple possibility that there might be another you out there. We've traced that idea from the basic geometry of an infinite flat universe, through the physics of eternal inflation, through the many worlds interpretation of quantum mechanics, through the mathematical universe hypothesis, and through the philosophical territory of identity, consciousness, free will, and meaning. The picture that emerges is one of extraordinary abundance, not a universe of scarcity, where existence is rare and precious by virtue of being singular, but a universe of unimaginable plenitude, where everything that can exist does exist, where every possible story is being told, where the pattern that is you is not a lonely singularity in a void, but one of an infinite family of instances spread across a reality larger than thought can reach. Is this terrifying? Maybe, at first. The loss of cosmic uniqueness feels like it should be a loss of something important. But think about what's actually being taken. Not your experiences, not your relationships, not your specific branch of the story. Those are all still yours, as real and vivid and present as they've ever been. What's being taken is only the illusion of a kind of uniqueness that was never actually there. The uniqueness you really have, the specific texture of this life in this branch, is real and yours and no less valuable for having counterparts elsewhere. And what's being added is something worth sitting with, a connection to the full scope of what exists. an understanding that the rules of nature, faithfully followed, produce you. Not because nature was aiming at you, not because you're special in any privileged sense, but because the same physical laws that make stars and planets and mountains and oceans and the emergence of life also make, inevitably, patterns as complex and aware as the one you are. In an infinite universe, that was always going to happen. The fact that it happened here, in this version, in this branch, is not luck, it's arithmetic. You exist because matter organized itself to a sufficient complexity in a universe with the right physical constants at the right point in cosmic history, and produced something that can look back at the universe and ask why. That process has happened infinitely many times, in infinitely many places, and is happening right now in ways you'll never see. But this version, the one you're in, is the one you get to experience, the one that is, from the inside, everything. That's not a small thing. That's not a diminished thing. That might be the largest thing we can say about what you are. The questions this raises don't end here, they multiply. If infinitely many versions of you exist, each equally real and conscious, what does that tell us about the nature of consciousness itself? Is consciousness a single thing that many instances share, or is each instance its own separate consciousness? And if it's its own separate consciousness, is there something to the experience of being conscious that isn't captured by the physical pattern, something that each instance has alone? That question, about what consciousness is and whether it's something more than its physical substrate, connects to everything we've discussed tonight and opens into territory we've barely begun to map. And that might be exactly where we should go next. If tonight raised more questions than it answered, the next video right here goes deeper into what consciousness actually is, why it remains one of the hardest unsolved problems in all of science, and what the answer might mean for everything we've talked about tonight. Thank you for staying. I genuinely hope something here landed in a way that stays with you.